Welcome everybody to the ODPi Egeria webcast. My name is Chris Blum. I do marketing for ODPi. And today we are going to be talking about Egeria and graphs. Graham Wallace is here from IBM to give you this wonderful presentation all about Egeria and graphs. Welcome, Graham.
Thanks very much, Chris. Hi, everybody. Yeah, I'm Graham. I work for IBM, as Chris just said, and I'm an open source developer and maintainer on the Egeria project, which is what we're going to be talking about, with a particular focus on graphs. I've been working on graphs and graph-related things for a while now, not a huge amount of time, about 5 years. So I'm still learning very much, but I'm very happy to share what I know with you. I hope you find it interesting and useful. If you have questions, I believe there is a chat running, which we're going to try and man. There are some other members of the Egeria team who will try and respond to your questions as we go through. If you can keep verbal questions maybe till the end, I'd appreciate it, because I've got a fair amount of material to go through. And if we don't get to your question, then please use the contact information at the end of the deck to get in touch with the team and ask your questions. We'll be very happy to work with you and talk to you. So yeah, let's talk about Egeria and graphs. Before we do that though, let's just do a little level set on metadata. Let's talk a little bit about metadata and about the realities in the commercial space, about some of the challenges associated with metadata. So first of all, what do we mean by metadata? So here's some data. The data should hopefully be obvious. It's a digital image. And the metadata is shown on the left. So to anyone who's familiar with photography, with cameras, particularly with digital cameras, then the metadata associated with this image could actually be quite useful. It will tell you all kinds of things like the type of camera that was used, the type of lens that was used, right down to things like the shutter speed that was used. And if we chose to, we could expand all of the EXIF data, and we could include things like GPS locations, which is an interesting point in itself, because when you take a digital image, you know, the camera will naturally capture a whole bunch of metadata, and it could optionally also capture something like GPS data, which I've deliberately left off this image. Now the birds in question in this image are not actually a protected species, but suppose they were, we may not actually want to give away their location, because there are people who would go and try and steal eggs or persecute the birds. And this particular bird, these are peregrine falcons, they were actually protected until 1999. And fortunately in the UK, they haven't been a protected species since then. But the point I'm making really is that there are things that you want to include in the metadata, and there are things that you might want to specifically exclude. You don't want to divulge too much information. And in the case of a digital image, the metadata is stored with the image file. But in a lot of cases, in commercial cases, they may well tend to be separate. They will generally be separate. So let's talk a little bit about, I mean, that was a very consumer-oriented example. But if we talk about the commercial realities of metadata and governance, what do people use metadata for in commerce, in a commercial setting? Well, they use it to describe all sorts of things. And these lists are in no way meant to be exhaustive, but they use metadata to describe database records and the schemas associated with those databases and records, files, the file formats, documents, models, AI models, training pipelines, etc. They'll use it to describe systems and applications. And in particular, something we've dealt with a lot on the Egeria team is processes like ETL processes from tools such as things like DataStage, for example. And also metadata describes the business concepts used by the commercial organization. And that will tend to be captured in things like glossaries of terms with different categories of terms, and also the semantic assignment of those terms to the technical artifacts like the database records, the things that are being described within the data. So moving away from our consumer-oriented organization, we're now sort of looking at the much more commercial reality. And the hard-hitting reality, the challenges that a commercial organization faces in terms of its data landscape, and the challenge of trying to describe it in metadata, is that these data landscapes are huge. They're very, very large, and they're distributed. The data is quite often dispersed across multiple data lakes. And each of those data lakes is serving a different part of the organization with different ownership, different geographical distribution. So we don't have a nice, neat single system which has got the data and the metadata co-located with it. What your average commercial organization has got is a vast landscape of data which is distributed across the organization. And there are multiple tools which are being used to create that data, to access it, to manage it. And so the real landscape looks far more like this picture, and this is a huge simplification, but you can see the heterogeneity in that there are lots of different repositories, and they're distributed, and there are lots of different tools from different vendors with different owners, which are being used by different communities within the organization. So you may have data scientists doing analysis, you may have data stewards, and all sorts of other specializations operating on the data and looking at very different views of the data and requiring different metadata. And this really leads to what we tend to term the Egeria manifesto, or the metadata manifesto, which I've reworded very slightly on this slide. And I'm not going to read through the whole thing, but basically to summarize, and you can find lots more about this on the Egeria website if you go to ODPi/Egeria. But just to summarize, the business users within the organization need to be dealing with the data in business terms. So they need a business-friendly, logical level interface. They don't want to be dealing with the kind of column names that we see in the average relational database. They need to be dealing with the business terms that describe things like customers, accounts, policies, addresses, those sorts of things. So a well-organized organization will have a common vocabulary or glossary, and they will also need to govern their data. And ideally, you want that data governance to be driven by the metadata. So it's absolutely essential that it's accurate and up to date. If the metadata describing our data assets, it gets out of date or has duplication or inaccuracies or poor quality, then you're not going to be able to drive a quality governance program off of that. So it's really essential that it stays accurate and up to date. And that really requires a degree of automation. Given the scale of the data and the data lakes that we've just been talking about across a typical modern organization, we really have to be able to automate. And you need multiple tools to be able to access the metadata and manage it. And this leads to the need for an open and remotely accessible framework in order to work with the metadata. We've got different tools in different locations with different owners. The tools are from different vendors. So we have a distributed computing problem, and we need open protocols, open types, and open APIs in order to allow all of these different things to work together and manage and automate the currency of the metadata such that we can drive a governance program off it. And that really, the last point about the open type system, the standardization, the open interfaces, is really the raison d'etre for Egeria. It's kind of why Egeria exists. So let's talk a little bit about Egeria. What is it? Well, basically, we're an open source project hosted under the ODPi project at the Linux Foundation. And Egeria is dedicated to making metadata open so that it can be automatically exchanged between tools and different platforms. It has an Apache 2 license, so it's very liberal, it's a very easy license. And the idea is really to enable both users, so the commercial users and vendors, so tools providers, database providers, etc., to create an open ecosystem for the management of metadata. Egeria really started from a number of years of work by people including, and this is not an exhaustive list again, but people like Mandy Chessel from IBM, from Shapers, or Schapers, I should say, from ING Bank in the Netherlands, and lots of other people. And that work all centered around data lakes, data governance, common information models. So there are some URLs here. If you haven't visited Egeria already, please do so. You can find the homepage, the first URL given there. If you're a developer or you're just interested in seeing more detail, all the code is up on GitHub, and we have very open governance of the project. So wherever code changes go in, you will find issues describing those changes. You'll be able to see the pull requests. So there is very open governance of the project and the code base, plus a wealth of information on that first URL. The community, the really active members of the community include IBM, ING, Manta, and SAS, the SAS Institute. And we also have contributions and interest from other organizations and individuals, probably too many to list here. So, excuse me, so if we go back to that view that we had just now of today's reality, where we have separate tools, we have disjointed metadata, we've got distributed data repositories from different vendors with different owners in different geographies, etc. Then how can Egeria help in this regard? And basically what it does is it allows us to create a federated, unified, and open view of the metadata across the different repositories, so that the different tools can now share that open and unified view. So whether you're developers or whether you're DevOps people or whether you're data scientists, and this obviously, you know, there are far more roles using far more tools than I've shown on this slide, but all of these different communities within the organization can have common access to a unified view of the metadata right across the organization, which is obviously quite a big challenge, but that's what Egeria is for. So it provides open type systems, open APIs, and it provides the ability to do federated queries across the organization, whilst allowing the data owners and metadata owners to retain control of their data and their metadata. So what you'll see topologically when you get into Egeria is a system where there are Egeria servers. These are just Java processes, basically, which are running and are communicating with one another across things that we call cohorts. So a cohort is a communicating group of servers, and the servers can perform multiple roles. A server can be a member of just a single cohort, or it could be like the server shown in the middle of this picture. It could actually be a member of multiple cohorts and actually passing data, passing metadata and events between the cohorts. Egeria servers can perform all sorts of roles. They can have local repositories, which we'll talk about a lot more later in this presentation. Or like the servers over on the right-hand side of this picture, they may not have repositories. They may be there to serve applications through things called access services. So you've got users like the data scientists, like the DevOps personnel, for example, using applications, using services on the Egeria servers to communicate with the other servers in the cohort. Alternatively, you go over to the left-hand side of this picture, we have Egeria servers which act effectively as proxies or bridges to external tools and repositories. So this could be an external tool, some kind of catalog, or a workflow tool, for example, and we can extract, we can query the metadata from that tool and make that metadata visible within a federated view that is constructed by Egeria. Okay, so these are just some of the terms that you'll see. Later in this presentation, I'm going to focus primarily on repositories because I'm going to talk a lot about the graph repository, but I just wanted to sort of give you the larger topological picture for now. So that's kind of overview, really. We talked about metadata, we talked about commercial reality, we talked about Egeria and what it does. But the main purpose of this session really is to talk about graphs in metadata. So here's a view which I stole from Mandy Chessel. which really shows how interconnected metadata is. And if you look at the bottom half of this picture, you see an employee record. So you can imagine this is a set of fields within a record in a database. So we have an employee name, an employee number, they maybe have a job code, they have a salary. So imagine you're looking at a database record. So this is structural data, if you like. Above that, above the horizon, up in the blue part of this picture, what you see is business concepts. So the business concepts are the fact that this person represented in the data may well be an employee who has a manager. They have an employee name, they have an employee ID, they have a job title, which is stored in the database as job code. But the terms that we're using up on the higher part of this slide are really the business vocabulary rather than the technical terms, the structural terms in the bottom. And you'll notice that also regarding salary, we can have business terms associated with compensation plans, which could either be an hourly pay rate or an annual salary. So you can represent choice at the logical business level. And very importantly, where we have something like a compensation plan, we can classify that. So we can associate a classification with that term, with the compensation plan term. So say, hey, this is sensitive information. So if someone is querying this data, you don't just go divulging everybody's salary to anyone who's querying the data. There may be some people in the organization who will be eligible to see that salary information or that hourly pay rate, to view the compensation plan for an employee, but not everybody. So the ability to associate a classification with a term at the business level allows us to do business level or logical level governance through things like policies, which we'll come to in a moment, which we can apply across all of the different forms of employee record down at the structural level within the data. So you can see that the business concepts in this picture form a very clear graph, a network, if you like, of terms with relationships between them, has-a, is-a type relationships. But there are far more graphs in metadata. And again, I stole this from Mandy unashamedly, because I think it's a very good pair of slides. So these are just a few of the other graphs that we see. So if we start in the bottom left-hand corner, I think we're all probably fairly familiar with the concept of a database, which has a schema. There can be tables in that schema, and there will be columns associated with each of the tables. And that forms a graph. Maybe slightly less familiar to us is the concept of a profiling tool, where we're analyzing the data within a database and coming up with a profile in order to optimize queries or to provide statistical analysis of the data in the database. Moving up to the top, let's start with the center, we've got the glossary category, glossary terms, which are the kind of things that we saw on the previous slide. And to the left, we talked very briefly just now, I alluded to governance and policies regarding that sensitive classification associated with the compensation plan for the employee. So a governance tool would tend to be based on strategy, policy, and regulations, which are implemented as policies, or from which we can derive policies, and then we derive rules, which we can then enforce on the data. And quite a common way of doing that is by having a classification on a data item or on a term. And any data which has that classification associated with it will be subject to the rules so that the policy is maintained. The top right as well, we have analytics tools. So we could be looking at a particular asset and analyzing the content of that asset in terms of its structure and the data within that structure. So a key point, which is across the bottom of this slide, is that it's very likely that you would be using different tools to perform all of these functions. And not only do we want to be able to query graphs within each of these separate graphs, but we also want to be doing queries across the graphs to answer the kind of questions that are in the little clouds. So can we be sure that when we're doing the profiling that we're looking at the same assets, the same database that we were talking about in the bottom right-hand corner? Does the glossary term get used consistently? Do we have a consistent business vocabulary with a glossary term that is used to describe the columns and apply the classification to the right columns? So you can see that we need to be able to do queries across different graphs. And bear in mind that also, as we said much earlier in this session, across distributed systems as well. So we need to be able to do queries across what's essentially a distributed and federated graph with all of these considerations. And we also see parallels between graphs. So if I focus on the left-hand side of this picture, first of all, if you look at the reddish pink boxes, they're really describing a database schema. We have some assets in blue, which are using a particular database schema. And that schema, in this particular example, happens to be a relational table or a set of relational tables, each of which have relational columns, each of which have column types. So if you follow the pink boxes down the staircase, effectively, from top left to bottom right, what you're exploring is the structure of that database. Now, in Egeria, we have a facility called Discovery, where it's possible to run an automated analysis across something like a relational database, as portrayed here, and to be able to discover the schema and to be able to report on it. And what we do is we create a graph, which is essentially a parallel graph, which it doesn't quite mimic the schema, but the shape of it does. So we have a discovery report with schema annotations, which consist of data fields, which are used to describe the tables, the columns, etc. So if you look over on the right-hand side of this picture, and this is not a great visualization, I apologize for the fact that it's not better, but the darker gray boxes, there's darker gray circles on this graph, are describing the asset and the database schema and the table and columns that we saw in the pink boxes on the left. And then the automatically generated discovery report is the paler gray vertices on the right. So the asset has a discovery report, and that has schema analysis annotations and data fields for the relational table, the relational columns, etc. So you kind of see how the graphs parallel one another. And we can do queries across both the discovery report and the schema information. So just to summarize around graphs in Egeria, as we can see from the examples that we've just been through with different tools, different business and technical metadata, and discovery analysis reports, we come across lots of graphs in metadata or graph-like structures. And Egeria is actually very heavily based on graphs and graph-like approaches. It includes a graph repository, which we'll talk about a lot more in a moment. And it also has graph-based tooling. So it has an open type system, and within the types, there is inheritance of entity types, and there is also, there are graphs of the possible relationship types that each entity type can support. I'll show you an example on the next slide. Excuse me. And also within glossaries and the glossary structure, we talked about glossaries, terms, and categories, and we use a graph-based approach to that, as well as the semantic assignment of those terms to the technical metadata. And also metadata instances. We'll see in more detail that we create instances of metadata to describe things like assets, databases, tables, columns, etc. So they become entity instances, and they are related by different types of relationship, and they're classified in the way that we saw earlier. And these very obviously form graphs as well. So let's look at a few examples. And these are examples taken directly from the Egeria user interface. So Egeria comes with user interface tooling, which we're still working on. It's still very much under development. But I wanted to include some of this to highlight the graph-oriented nature of a lot of what we do. So the left-hand picture here, the one with the kind of aqua blue or turquoise header here is a screenshot that I took of our type explorer. So what this is basically an inheritance graph of the entity types. So this is saying that asset, which I don't know if you guys can see that clearly, I hope you can, but asset has subtypes of dataset, data store, deployed API, and so on. And so the tooling is very much graph oriented. When you're in the Type Explorer tool, you can click on nodes within this graph and expand and contract the nodes. So it gives you a really easy way of navigating through the open metadata type system. Over on the right-hand side is an example of an instance graph. So this is from the Repository Explorer page of the user interface. And so this is saying we have a data set which has certification type. Now actually has two certification types. Associated with one of those, there is a note log entity, and that has note log entries associated with it. So all of the vertices in this graph are entity instances from within repositories that Egeria is querying across. And the relationships are, they're not labeled in this picture, but they are the relationships such as things like the note log contains and note log entry, for example. They're just not labeled in this particular picture. So both the Type Explorer and the Repository Explorer give us graph-based exploration of types and instances respectively. And then the picture in the middle is something I'm working on at the moment, which is an admin UI. And this really shows you the deployed topology of Egeria platforms, servers and cohorts. So what this is showing is that in the topology that I ran this against, there are two platforms, which I imaginatively called Platform 1 and Platform 2. Platform 1 is running a server called Metadata Server, and Platform 2 is running a pair of servers. One is Metadata Server 2, and the other one is View Server, which is the server which is actually supporting this particular admin UI. And then the two servers, Metadata Server 2 and Metadata Server, are both members of the same cohort, which is called Dev Cohort. So a graphical representation here is very useful, and it shows us what's running where, which servers are members of the same cohort. So you can very quickly explore the topology and get a graphical view, as well as this textual view on the left, through which you can explore the configuration of each of the servers. You can see what cohorts they're in. You can see which other servers they can see within those cohorts, and you can see what services they're running, what services are deployed to the platforms, etc. So we make very heavy use of graphs within our UI. And the glossary, I haven't shown a picture of the glossary authoring UI here, but that will be similar again. An important point about Egeria, I mentioned right at the beginning that we're dealing with distributed data. So imagine that we're serving a large organization which has a number of data lakes spread internationally around the globe. And so there are repositories of data, and particularly metadata, which are spread out. And it's just not feasible to pull all of that stuff together into one repository and one tool which is going to allow you to query it. From a scalability point of view, from an ownership point of view, and from a regulatory point of view, that really doesn't make a lot of sense. So what Egeria does is it allows us to federate metadata from across multiple repositories. And it does that transparently. We'll talk about that a bit more in a moment. But the key thing I wanted to make, the key point I wanted to make here is this gives rise not just to a graph, but to a distributed graph. So the vertices and edges that we're dealing with when we look at those instance graphs and with the topology graphs, etc., are not all vertices within a single graph repository. These are distributed across networks. And Egeria is able to create relationships between entities that are in different repositories. And two entities that are related don't have to be in the same repository. They can be distributed, and the relationship can be in either of those repositories or indeed in a third repository. And we'll go through some pictures of that in just a moment. And Egeria has this federation capability. It has what we call an enterprise repository layer, which allows us to query and traverse the different repositories as if they were co-located. So it overcomes the distributed nature of the metadata. Now, the important things about this are that rather than picking up the data and moving it to another location, ownership remains with the current owner. So if we have a particular tool that we use to manage a particular set of data within a data lake, and we're managing the metadata for that data through that tool, and it is owned by a certain part of the organization, then we're not saying, oh, sorry, you've got to lift and shift that to some other part of the organization. The ownership remains with the current tool, with the current owner, which is really important. And it also minimizes the risk of duplication or the risk of updates being applied. If we started copying metadata around all over the place, i.e. not doing what Egeria does, but if we manually copied metadata all over the place, there would be a real risk that we get divergent updates on copies of that metadata. And Egeria avoids that, as we'll talk about in just a moment. So it can create copies of instances for local caching and for performance. But it never takes ownership of the metadata when it does that. The ownership remains with the tool and repository that created the instance originally, or that has been designated as the host, the master for that instance of metadata. And Egeria will only permit updates on that owner's original, not on the copies. So the reference copies cannot be updated. You can't update the properties of them. And when Egeria accesses a remote instance, it has a protocol at a level called OMRS, which again we'll talk about in a moment, which registers interest in the remote instance. So if there is then subsequently an update to that remote instance by the owning repository or tool, then any registered Egeria servers will receive events delivered to their access services so that they get to see the fact that the master copy, the original copy, has been updated. So the OMRS protocol allows us to maintain currency of the reference copies. And it is possible to transfer ownership of an instance if necessary, but it's not something that you need to do. It would only be if, for example, you are going to retire a given tool or repository and you explicitly want to change the ownership of the metadata to another repository, in which case it is possible to do that. So you can migrate ownership. So some graphical examples, which I think make it a lot clearer rather than listening to me talking about it. Imagine we've got two OMAG servers, they've got repositories, and they store two separate entities or entity instances. So one on the left has a database column, and the one on the right has a glossary term. Now we want to create a relationship between these two distributed entities. One way of doing it is that we take a reference copy of the glossary term and we store it on the left-hand server. So the one on the right is the original glossary term. We cannot modify the reference copy of the glossary term. We can create relationships to it, as we'll talk about in just a moment. And we can also classify it if we need to. But the glossary term on the left is a copy. It is not the authoritative instance, which is the one on the right. And so we use the OMRS protocol to keep it up to date. And then within OMAG server 1 on the left, we can create a relationship. In this case, it's a semantic assignment. So it's saying the meaning of the glossary term is that it describes this database column. So in this case, we've taken a reference copy and co-located it with the database column and created the relationship locally. We don't have to do that. We could do what's in this picture, which is we've taken reference copies of both the database column and the glossary term, and we've created a relationship on yet another server, OMAG server 3 in this case. So it's very flexible. And actually you don't need to take reference copies. So in case you're wondering, it's quite possible to just leave the database column and the glossary term in their owning servers, owning repositories, and in another repository if necessary, so under OMAG server 3, we can use what's called an entity proxy, which is effectively a pointer to the glossary term or a pointer to the database column. So the proxy will store the identity of the metadata collection where the authoritative instance exists. And then we can create the relationship wherever we want to. So what we're building here is a distributed graph. The entities can be in different servers. The relationships can be in different servers. And we can also classify entities as well. Okay, so what I'm going to do now is we've talked about the distribution, we've talked about the federation, we've talked a little bit about the OMRS protocol. What I'd like to do now is to dive down a little bit into OMRS so that I can describe the graph repository to you. So I'm going to go through a few slides of Egeria internals and then get to the graph repository. So bear with me. Okay, so Egeria, as we've said, it has local metadata repositories, or it includes metadata repositories, which come as part of Egeria. You don't have to use them. You can always go back to the authoritative source and query and use that federated query mechanism in order to be able to find the metadata. But sometimes it's going to be more performant to have taken a local copy. And there are times when there may be functional gaps between other tools and repositories. And actually it's better to map the remote metadata into an Egeria repository, which has full support for the Open Metadata type system, for example. And so we have an Egeria provided repository, which is storing reference copies. Now, one of the repositories is a graph repository. And the reason for having a graph repository in Egeria is it is obviously a good fit for the kinds of queries that we saw earlier from all those graphs, the distinct graphs, and then the graphs where we were querying across, doing traversals across the distinct graphs. So the graph repository is really helpful to us. Let's talk a little bit more about OMRS, just so that we understand where we are in Egeria when we're talking about. So on the right, we have a picture of a server, which is a member of Cohort. And the OMRS layer, which we saw on the previous slide, really kind of splits into three. There's the enterprise connector layer, and this is what gives us the federated capability. So this is able to do remote queries and aggregate the results. It's also what's responsible for registering the interest in the reference copies or triggering the creation of that interest so that we get events when things get updated. We then also have a local connector and event mapper, which is able to perform operations locally and also to manage events, propagate events that we see from elsewhere. And then below the line there on the right, we have what's called an OMRS repository connector. And that is Egeria's method of interfacing to a specific repository. Now we have two built-in repositories in Egeria. One is the graph repository, which we'll talk about. There is also a non-persistent repository called the in-memory repository. And it is possible to create connectors for other types of repository. So for example, if we wanted to implement a relational repository, we could do so, and we would just be creating the repository connector, i.e. this layer, in order to plug in that relational repository into the OMRS. And the interface to the repository connector is this thing called the Metadata Collection API. So we tend to think of things as collections of metadata. So the metadata collection interface has a lot of operations, as anyone who's implemented a repository connector will tell you. There are 6 groups of operations. The first one is very straightforward. It is really just about identification of the repository, which is by a GUID called Metadata Collection ID. So that uniquely identifies this metadata repository on the network. Group 2 is all about types. So it's about type definitions, it's about attribute type definitions. You can add them, you can find them, you can retrieve them, you can remove them. It's also possible to update types as Egeria releases come out. It's possible to ship type patches or new types. The third group is the ability to find things. So this is what we're doing when we're doing graph queries, whether they're purely in the local repository or whether they're at the enterprise level and going distributed. We can do searches across entities and across relationships, and this is quite a flexible interface. So you can search for entities filtering by type or filtering by property values. You can do the same with relationships. You can also search for entities that have a given classification or have a given type of classification that has a certain set of properties. So it's quite a rich search interface. Group 4 is all about maintenance. So this allows us to create instances of entities and relationships, to classify them, etc., and delete them. Group 5 allows us to change control information. So we talked about being able to change the ownership of an entity instance earlier on. Well, that's the rehome operation. So we can pick up the master copy of an entity instance from one repository and assign that ownership to a different repository if we need to. It's not something you routinely need to do. It is also possible to re-identify things as well and retype things. And in group 6 within the metadata collection interface is all about maintenance of what we term reference copies, the replicas that we talked about earlier. So they can be created and they can be purged and they can be refreshed using the reference copy refresh protocol within the OMRS. So it's quite a rich interface. There's a lot going on. But we've implemented a repository connector which interfaces to Janus Graph. So this gives us a persistent graph-based repository. The non-persistent repository mentioned here is the in-memory one that I mentioned previously. But the persistent one is built on Janus Graph. It's actually built on Janus Graph 052 currently, and we keep updating that as Janus Graph evolves. Why Janus Graph? Well, we like it. It's another Linux Foundation project. It's a very capable database. It implements the Tinkerpop graph model and APIs. It has a very compliant license. It's Apache licensed. So it is a very obvious choice for us in terms of being having the function that we need and also being part of a well-governed and active community. The Tinkerpop community is created through people like Stephen Mallet and Dan Cuppets. And the Janus Graph community as well is extremely active, and it's a good database for us to choose. So the way that we plug in a repository to Egeria is using a plugin pattern. As I mentioned before, we create a repository connector, and we tend to term that as the plugin pattern. So the graph repository can store instances of metadata that are owned by the local server. It will also store reference copies of metadata replicated to the local server, and it will also support relationships and classifications, etc. And the graph connector polices the fact that a reference copy must not be changed. So we can create relationships between reference copies or reference and non-reference copies. We can classify them, but the graph connector will prevent you from inadvertently trying to change the properties of a reference copy. Obviously, while we're fans of Janus Graph, it's not the only graph database available. Others are available. And it would actually be quite straightforward to create repository connectors for different databases. I mentioned just now that we could, for example, include a relational or a column-oriented repository. Also within the graph space, you know, if we wanted to, we could create a repository connector for any other graph database, and there are plenty of them. You know, I won't list them. Folks who are familiar with graph technology, I'm sure, would reel off a long list. I can think of probably about 15 off the top of my head. So if someone had a requirement that they always use a particular graph database, then it would be possible to create a repository connector for that particular graph database. And when people create connectors to databases to create new repositories or connect to new repositories, we have a thing called a conformance test suite, which runs an automated set of tests, which is, I wouldn't say entirely exhaustive, but it's pretty good. And you can run that against a repository, and it assesses whether it correctly implements the open metadata types and whether it correctly implements the metadata collection API. So it essentially gives you a score. Some of the, when we were talking about the metadata collection interface just now, I should have mentioned that some of the operations are mandatory and some are optional. So you don't have to support all of the operations in order to be conformant with the Egeria interface. But obviously, the more of the optional ones that you can support, the better, because we can provide more function to the users. So there is this automated test suite to enable us to test repository connectors. So let's talk much more specifically about the graph database, the graph connector. So we saw the picture just now, which had the layers of OMRS. So we had the enterprise connector, which is for federation, etc. We've got the local connector, the event mapper, which is dealing with events coming in and out on the cohort. And then we've got the graph connector. And beneath that, we have a thing which is, again, that's Egeria code. So it's the graph metadata store, which is what actually maps from our metadata collection API to the Janus graph APIs. And then in the green here, this is non-Egeria code. This is basically all Janus graph. So we've got the Janus graph core engine and Janus graph management component, which is how we do schemas and create indexes, etc. And we also have the Apache Tinkerpop interface. And now when I wrote the graph metadata store, I tried wherever possible to use the Tinkerpop functions, to use Tinkerpop APIs, so that we are as standard as possible. And if we wanted to implement another graph database, which also supports Apache Tinkerpop, then we would have as much common code as possible, basically. So from a database portability point of view, we've tried to maximize our use of the Tinkerpop APIs and try and avoid doing things which are Janus graph specific. Having said that, there are some things, some of the search predicates, etc., and obviously the schema management under the Janus graph management component, they do tend to be specific to each graph database. So we can't be 100% portable at the graph metadata store level. Now Janus graph has two types of backend. It has a persistent store, which is where it actually stores the vertices and edges that we write into the database. And it also has an indexing backend or a search backend. And those are pluggable. So Janus graph will let you use a choice of persistent stores and a choice of indexing backends. The first release of the Egeria graph repository used Berkeley DB for its persistent backend, and it uses Lucene for its indexing backend. It's quite nice in that this is an entirely embedded topology. So you just need to start the Egeria server with the appropriate config. You set the repository mode to graph, basically. I'll show you that in a minute. And when you start the server, if we haven't already run that server, a Berkeley database and a Lucene backend will both be, a Lucene index will be created and will be used. So it's very good for quick start. It's great for development and testing. And it's probably sufficient for some production uses. However, it may also be desirable to use different ones. So for example, ING Bank have already extended the Egeria graph repository so that we can configure it to use Cassandra, and we can use Elasticsearch as alternatives to Berkeley and Lucene. And they use remote services, so they've got a Cassandra service, they've got Elastic services. So these are managed services, and they hook their Egeria graph repository onto those. So they did a really nice job of adding to the Egeria configuration, the graph configuration, to enable that. It would also be possible to use Solr, obviously, and to use alternative backends I won't bother to list all the ones that you can use with Janus Graph. And we're also starting to discuss doing an additional piece of work which will allow us to remote the Janus Graph server piece itself. And that would be nice because it will allow us to provide an HA option. So you'll be able to have multiple servers up and running. If we have a system failure, then we'll be able to pick up and carry on through an alternate Janus Graph server. So the initial implementation was very much quick start. And as people are using this more, we're expanding it more and allowing more permutations. So inside the graph repository, there is the connector. There's also the connector provider, which you have to write in order to new up a connector. We've then got the metadata collection class itself, which is that metadata collection interface, that API. And just beneath that is the metadata store, which maps us onto the graph database. So if you look carefully at the in-memory repository versus the graph repository, you would find that the top 3 layers here are very, very similar. And it's when you get down to the metadata store class where you really start to see the differences, because the connector that I wrote maps to a graph database. The in-memory metadata store is mapping to a set of in-memory maps. So that's where you really start to see the difference. Other important classes within the graph repo, graph repository components, include the graph factory. So this is how we actually create the graph database, how we initialize a schema, create the indexes. And that tends to encapsulate all the Janus Graph specifics, other than things like text predicates, case-insensitive text searching, and that sort of thing. And then there are a bunch of mappers. So these give us the ability to map an entity to a vertex or a relationship to an edge, for example. And I'll show you more of that in a couple of slides' time. So how do you use it? How do you start up a server and get it to run a graph repository? Well, basically, when you're configuring your OMAG server, that's Open Metadata and Governance, by the way. When you configure your OMAG server, you just set the repository mode to local graph repository. And you can do that by posting to that URL. You can do basically post-based configuration. So if you set the repository mode to local graph repository, then when you start the OMRS instance in the server, then basically the graph repository connector provider will create the connector that will trigger Janus Graph to create persistent backend, the search backend. It will initialize the graph schema, and it will create search indexes on all of the types that it supports, which is the whole of the Egeria type system. So it's actually very simple to get going. You don't need to do, if you're using, certainly if you're using Berkeley and Lucene, using the embedded configuration, you don't need to do a lot of setup of the backends or anything. It's very straightforward. We're going to talk a little bit about the graph schema, but I wanted to put a warning on this slide, which is that really the metadata collection interface is the formal interface to an Egeria repository. So once we've gone through that startup, configuration and startup pair of steps that I showed you on the previous slide, we will have created a Janus Graph database. You could obviously at that point hook a Gremlin console onto that Janus Graph and go and have a look around, and you'd be welcome to do so. If you have any feedback for me in terms of what you find there, then I'd be very interested to have a chat. But one thing I wanted to sort of warn is, please don't rely on the schema. I don't write any other tools or applications or anything which are relying on the graph schema, because as a project, we, the Egeria community, reserve the right to evolve it for performance reasons or to introduce new features, for example. So it's really the metadata collection interface, which is the formal and open interface. There's a couple of points here about type data and instance data with regards to the schema. So we don't store type definitions. We delegate all of the type operations to a thing called the repository content manager. And this is great because otherwise we would be implementing this per type of repository. So every repository connector would have needed to worry about all the types. So there are, as you look at Egeria, you'll find there are lots of places where we've distilled function into helper classes and manager classes. The repository content manager is a really good example. So within the repository connector, we don't need to do things like type verification and things, because that's all done for us by the RCM, which is another part of the OMRS layer. So what we do store in the graph database is instance data. So this is entities, relationships, classifications. So we use vertices for both entities and classifications. I'll show you this pictorially on the next slide. And we use edges within the graph database for relationships and classifiers. So suppose that we were looking at this, this model. So what this is showing is we have a pair of entities, which are the white ovals with black borders. So we've got a pair of entity instances which each have attributes, which could be primitives, they could be enums, they could be collections, but there are attributes associated with those entities. There's also a relationship between them. So this kind of greeny box is depicting a relationship between the two entities. And that relationship itself has attributes, which could again be primitives, enums, or collections. And one of the entities is involved in this relationship is classified. Now that doesn't mean classified as in it's top secret. It means it has a classification, which could mean all sorts of things. So it could be to do with confidentiality, but that's only one possible classification. It could also be a classification that tells us which zone or zones this entity is visible in, for example. And there are all sorts of other reasons for classifying things. So classification is a very general term. And classifications themselves can have attributes, which again can be primitives, enums, or collections. So those are the kind of concepts that we're trying to represent. So how do we represent that in a graph database? Well, some of it's obvious, maybe quite so. So a classification instance becomes a vertex, and its attributes become properties on that vertex. An entity instance, again, becomes a vertex, and its attributes become properties on that vertex. And when we have a relationship instance, we create an edge within the graph, and the attributes of the relationship become properties of that relationship, of that edge. And we use a different type of edge, different label for relating entities to their classifications. I use the label classifier, which again becomes an edge with properties. And so our original picture, when we map it into the graph database schema, turns into this. So we have the same pair of entities, but implemented as graph database vertices. We have a relationship edge connecting those two entities, and we have edges going to the two classifications. So classifier edges going to the two classifications. And we can associate properties with all of those vertices and edges. I think actually in the graph repository in Egeria, I think I never make use of properties on classifiers because we never share classification vertices. A classification vertex is always specific to the entity that it classifies. So the properties of the classification exist on the vertex, not on the edge. I think this slide really just summarizes what I just said. The only differences are about reference copies and entity proxies. So if something is a reference copy, then its metadata collection ID, which is a property of the vertex, property of the edge, will be set to the GUID, the metadata collection ID of the home repository, not necessarily the graph repository in which it's been stored. So we know where the owner is, basically, and we know that this is only a reference copy, and we will not update it when we shouldn't. Similarly, with entity proxy objects, the vertex, any vertex that's being used to represent an entity proxy just has an additional property, which is of type Boolean, which just tells us whether it's a proxy or not. If you think back to those pictures where we were doing the distributed relationships between entities. So there are various types of query that we support within the metadata collection interface, various types of graph query. So we can get all the related entities associated with an entity. So the little blue arrow on this diagram is really the starting point. It's saying we're starting at this entity, and we can get the entities that are directly related to it. So we will pick up these 4 entities here. Get entity neighborhood, you can specify the depth or the level to which this, this traverses. But again, starting at the same entity, if we said get the neighborhood to a level or depth of 2 around this entity, then we would pull in all the entities and relationships shown in this diagram in green. If we got linking entities, then basically this is like a connected path. So we're saying starting here and finishing here, find us all the relationships and entities that connect this entity to this other entity. And get relationships for entity basically says, don't worry about the neighbors, but I am interested in the relationships that this entity has to other entities. And so we can extract just a set of relationships. So those are really useful queries where we're wanting to explore the structure of the metadata graph. Particularly things like the neighborhood query is one that we use a lot. And being able to traverse across the graph from a start point to an end point, obviously, is something which is a lot easier to do with a graph database than if you had to code all that by hand. So the graph repository supports almost all of the metadata collection API. There are a couple of optional aspects which it doesn't. So it supports all of the operations on reference copies. It supports entity proxies. It supports delete and restore as well as purge. So there are 2 types of delete. There's soft delete and purge. So soft delete doesn't actually remove the vertex or the edge. It is restorable. So you can do a soft delete and you can then later come back and go, actually, I'd like to restore that vertex or edge. And so it can do that. It can undo a soft delete. But if you do a purge, then that is permanent. So that will actually get rid of the vertex or get rid of the edge from the database. The graph connector graph repository supports retyping of instances, re-identification of instances, the rehoming of instances that we talked about earlier. It supports the 4 graph queries that we saw on the previous slide, and it supports find methods. So this is find entity by property, or find relationships by property, or find entity by property value, find relationships by property value, and find entity by classification. Now, since I wrote this slide, there are actually 2 new find methods. There's find entities and find relationships, which Chris Grote very kindly added, which are a much more versatile, more flexible pair of find methods in that you can do things like range queries and that sort of thing. And we haven't yet added those to the graph connector, but we're due to. So, so if you wanted those, then watch this space. If you'd like to have a go at implementing them, then you'd be very welcome. Things that the graph repository does not yet support include historic queries. So the metadata collection API has the ability to do things like a find method where you can set a historic time parameter. So you can say, find me all the instances that have the following criteria. You know, you can specify properties and types, classifications, etc. But I'm interested in what the repository looked like an hour ago or a week ago, for example. So you can set a historical time and say, show me the answer that you would have got at that time. We don't yet support that in the graph repository. Whether we will or not, I'm not sure. Including history in a graph database is an interesting topic of discussion. If anyone has any ideas on that, I would be very happy to chat through what I perceive as the problems with doing that. It'd be a great thing to be able to do. I would love to be able to say, hey, let's go back in time a week and see what the repository looked like then. But from a scalability point of view, that could be quite challenging. The graph repository also does not yet support the undo operation. So basically, there is a set of undo operations in the metadata collection, or the ability to undo certain operations within the metadata collection API. And the graph repository does not yet support the ability to do those undos. That's something which is kind of related to the historic query capability as well, for obvious reasons. Okay, that brings me to the end of the slide. So I just wanted to include this slide for more information. So basically there is the Egeria project website, which has got tons of material. It's got lots of documentation. It's got architectural material. It's got material on how to get involved in the project. It's got developer guidelines. If you wanted to contribute to the project, then you will find everything you need in terms of how to get started, how to clone the Git repo, the contributors license agreement, all of those sorts of things. are all up there, as well as lots of architectural and usage information documentation about Egeria. There's also the GitHub repo. That's kind of where all the code lives. You'll find all the issues, all the pull requests. And as I said at the beginning of this presentation, we try and be extremely open in terms of our project governance. So we record our calls, we document everything as far as possible as issues, we debate things online. So there are no kind of secret discussions going on behind the scenes. We try and be as open as possible. And we also have a Slack channel. So you can get us on Slack using the ODPi Slack channel. There are a whole load of discussion channels there. So please go use those sources of information. If you want to ask us anything, Slack is probably the best way to do it. If you try Egeria and you find that things are missing, feel free to raise an issue. We're not averse to people raising issues on GitHub. It's a very good forum for discussion of requirements and to give us traceability through to a pull request that satisfies the issue. So with that, I will wind up and hand back over to Chris.
Thank you so much, Graham. So we did get a question about the webinar, and it is being recorded, and it will be on our ODPi YouTube channel later today. There's some great materials there as well. Thank you so much, Graham, for your in-depth and thorough presentation today.
It's a pleasure. Thank you.
And we will have another webinar covering all the ODPi projects on September 22nd. We'll be sending out an invite to that later this week, so keep an eye out for that. Thank you, everybody, so much for joining, and have a wonderful rest of your day.
Thank you very much, Chris.
Thank you.